In this video, we are going to talk about hypothesis testing for a proportion. This is our overview slide, which we'll spend about 10 minutes going over before we go over each topic in more detail and with more examples. In hypothesis testing, we're trying to verify the validity of a claim, which we often call the alternative hypothesis, or H of A. It's an alternative to what we know now, or the status quo. So the competing hypothesis is called the null hypothesis, the H naught. It often represents a skeptical perspective of something new, like HA, or that, there's really no difference, nothing new to discover. It's a very skeptical perspective, and it is, again, the opposite of the alternative hypothesis. The null hypothesis represents the status quo. The alternative hypothesis says, no, there's something new. There's this alternative to the status quo. So it's an alternate claim under consideration, but as data scientists, we have to play the role of skeptic. We don't want to jump on every bandwagon because someone says they see something new. Before we buy into something new or the alternative hypothesis, we need to see strong supporting evidence. One of the big things when we arrange or define our null hypothesis versus alternative hypothesis, we have to consider decision errors. So if we decide the alternative hypothesis is true or the null hypothesis is true, we want to know what is the cost of errors, because often some errors have worse consequences than others. The sort of canonical example everyone gives you is the United States system of justice. Usually we like to err on the side of pronouncing people innocent. So when they go through the Justice Department, when you go on trial, you say you're innocent unless people can prove that you're guilty beyond a reasonable doubt. In other words, our competing hypothesis then is that the person is innocent or the person is guilty. And we want to choose such that the alternative hypothesis is something that we need strong evidence to accept. So again, this is one. We need strong evidence to accept HA. So that would mean we want strong evidence before we pronounce someone as guilty. So that in this case, HA would be guilty and H naught would be innocent. Now let's look at these types of errors. So we can either conclude that we do not reject H naught. And remember, this means do not rejecting H naught means we don't conclude that they're guilty. Or we reject H naught and we accept HA. That would mean we say they're guilty. I've written my notes of what H naught and HA are next to my things here. So in this example, accepting HA is to give a guilty verdict. Here, the truth is whether or not the person is innocent or guilty. If H naught is true, that means they're innocent. If HA is true, that means they're guilty. Over here, you notice I don't say we accept H naught that they're innocent. It's not that we totally know that they're innocent, but we don't reject it. In other words, we think they might be innocent. I tried to write that in here. Now, this matrix tells us whether or not we've made an error. So here, if we say, well, maybe they're innocent and they're actually innocent, then we've made a correct decision in reaching a verdict. If we come over here and said, no, our conclusion was that they were guilty when they were really true, that would be an error. And that's what we call a type 1 error. Type 1 error is rejecting the null hypothesis. So saying that HA is true when H naught is actually true. Okay, so we're saying HA is true, but in actuality, H naught is true. That's a type 1 error. Over here, we can decide, maybe a jury says, well, maybe they're innocent when actually they're guilty. So that would be an error. This is what we call a type 2 error, and that's when we fail to reject the null hypothesis when the alternative is actually true. So HA is true, but we don't come and give them a guilty decision. And then our last thing is if we decide they're guilty and they actually are guilty, that's another correct decision. So there's type 1 and type 2 errors over here. And we want to choose, when we choose HA, so that we need strong evidence to support HA, we are minimizing the type 1 errors. And in this case, the type 1 error is convicting an innocent person and saying they're guilty. So again, strong evidence to support HA. When you choose it that way, you minimize type 1 error, which is to reject the null hypothesis. In other words, go with the HA, the alternative hypothesis, when the null hypothesis was actually true. To summarize, we're going to choose H0 and HA so that we need strong evidence to accept HA, and therefore we're going to minimize our type 1 error. In our decision making, we want to use probabilities. So we're going to do hypothesis testing using confidence intervals. Confidence intervals was the topic of our previous video. If you've forgotten, I totally recommend that you go over it. So in our confidence interval, we're going to use our sample statistics p hat as an estimate of our population parameter p. And the mean of our probability distribution then will also be p hat. Also p hat is what we use to calculate the standard error. Then we use z-scores to determine the interval where we are XX% sure, so maybe 95% confident that our population proportion p is in this interval. And we'll do examples of that. So again, this is really kind of combining, throwing in things from the last video. But there are examples where confidence intervals cannot be constructed, so we use p-values. So this is very similar, but what we do is the p-value is the probability of observing data at least as favorable to the alternative hypothesis as our current data set, if the hypothesis were true. So what we do is we assume that our null hypothesis is true, and we use our proportion from our null hypothesis, and that's going to be the mean of our null hypothesis distribution. And then we can then go and do our confidence intervals based on our null hypothesis. So when the p-value is less than the significance level, which we call alpha, we reject H0 and we report a conclusion that the data provides strong evidence supporting the alternative hypothesis. And when the p-value is greater than the significance level, which we designate as alpha, we do not reject H0 and report we do not have sufficient evidence to reject the null hypothesis. So we'll do examples of this as well. So that concludes our overview. So we'll go back up here and look again at the null and alternative hypothesis. The null and alternative hypotheses are literally competing hypotheses. So in other words, you have this idea, this new exciting idea. It's an alternative hypothesis. The null hypothesis literally says, oh, that alternative hypothesis of yours, it's wrong. Or you could say that you have this null hypothesis and the alternative says, oh no, that null hypothesis is wrong. Literally competing ideas. The idea though, is that the alternative hypothesis represents something new, something different. The null hypothesis represents sort of the status quo. It's skeptical of new things, so it tends to hold on to the status quo. And then the alternative hypothesis represents the alternative claim under consideration, and our job as a data scientist is to play the role of the skeptic. Before we buy into something new and exciting, we want to see some strong supporting evidence before we disrupt our status quo. And as I alluded in my introduction, we don't really choose the alternative hypothesis as what's necessarily new and exciting or what we want to, like what we're rooting for. It's, again, the one that we're going to be skeptic of. And the kind of canonical example is the U.S. courts. When we look at claims by the defendant, there are two possibilities. Either the defendant is innocent or guilty. So if we set up these claims in a hypothesis framework, which would be the null hypothesis and which would be the alternative? And in the U.S. justice system, we assume innocence unless we have strong evidence otherwise. So we're skeptical then of guilt. We don't want to jump to the conclusion of guilt. So we would set up that H0 is innocent. That's the one we tend to want to stick with, and the H0 is the one that we are skeptical of, and we need strong supporting evidence before we accept the alternative hypothesis of guilty. Similarly, if you're testing whether a new drug is better or worse than an existing drug treating a particular disease, what should we use for the null and alternative hypothesis? And this is where you want to think, okay, Your alternative hypothesis, that's where you want to be a little skeptical before you introduce some new drug treatments. So H0 is going to be the claim that the new drug is no better or worse than existing treatments, and HA, the alternative, is going to be the new drug is better or possibly worse. Basically, it's different. Our next example, we are interested in how many college-educated adults can answer the following question correctly. How many of the world's 1-year-old children today have been vaccinated against some disease? And it's a multiple choice question. A is 20%, B is 50%, or C is 80%. The correct answer, by the way, is 80%. So how many college-educated adults can answer this? And you also want to note, if they randomly guess, there's 3 possibilities, so there's a 1 in 3 chance of randomly guessing a correct answer. So this is what we're going to say is our null hypothesis. You know, maybe they really don't know, and they're just sort of guessing randomly. That's the uninteresting kind of status quo. The more interesting or new kind of thing you want to be skeptical of is that the proportion is not equal to 33% or 0.33. And this hypothesis is set up. We want to make a conclusion about the population parameter, P, over here, and the proportion of college-educated adults who can answer the question correctly. It is unlikely the proportion of people who get the correct answer is exactly 33.3%, and for that reason, we use a confidence interval. But before we go through that, let's take a closer look again at setting up our null and alternative hypothesis by examining different types of errors. So here we're going to look at decision errors, and often there are some errors that have worse consequences than others. So we want to choose H0 and HA to minimize what we call type 1 errors. And type 1 errors is when H0 is true, but we jump to HA. And remember, we want strong evidence now to support HA. So let's take a closer look at that. So now we have a decision. Either HA or H0 is true. Remember, they're competing hypotheses, so only one is true. So in my table here, I have the 2 possibilities. Either H0 is true and H1 is false, or HA is true and H0 is false. We can run our test, and this is what we decide to do. We can decide to accept H0 and reject HA, or we can decide to accept HA and reject H0. Now we want to determine if we've made a mistake or not. So if we come over here and read on this line, the first row, this is when H0 is true. So if we accept H0, we've made a correct decision. If we accept HA instead and reject H0, we've made an error. Don't worry about type 1 for now. If, on the other hand, HA is true and we accepted H0 and rejected HA, we've made an error. And if HA is true and we accepted HA, we've made a correct decision. So there are a couple of things to say. First, we never get around to exactly accepting H0. And the reason is we favor it so heavily, it would be kind of a strong thing to say that we're absolutely certain that H0 is true. So what we do instead, we don't accept H0, but what we say is we don't want to reject H0. In the example of whether or not someone's guilty or innocent, we so much protect the innocent people that we tend to err on saying that they're probably innocent. You may not know for certain that they're innocent, but they probably are. So that's what this means over here. We don't want to reject, flat out say they're not innocent. We may not be 100% sure they're innocent, but we're not going to say they're not innocent. So H0 is so favored, we never actually accept it. We just say we did not reject it. But in essence, it kind of leans towards accepting H0 and rejecting HA. Okay? The next thing then is, now that we have this grid, there are 2 types of error, type 1 error and type 2 error. When H0 is true, and we accepted HA, that's considered type 1 error. Whereas when HA is true and we did not reject H0, that's a type 2 error. And we want to make our H0 and our HA to minimize type 1 error. So I'm going to circle that. So that's important. We minimize type 1 error, and we do that by requiring strong evidence to accept HA. So in future charts, I'm going to get rid of this matrix here because usually we really don't accept H0. I just wanted to show you what the pure kind of matrix would look like, but this is actually sort of the what we actually do. And again, reconsidering our U.S. court system, the defendant is either innocent or guilty. How should we arrange the null hypothesis and the alternative hypothesis? And we only want to accept HA if there's strong evidence. So we only want to produce a guilty verdict if there's really strong evidence. Otherwise, we're going to lean towards innocent. And kind of just adding this interpretation now, the H0 here, to this matrix, the truth is H0 is that he's innocent, HA is that they are true. Then this first type of correct decision is we do not reject H0. So we're going to say, they might be innocent. We don't want to jump to HA. We're going to say they might be innocent. And if they are innocent, then we've made a correct verdict. If they are innocent, but we reject H0, that means we accepted HA, we said that they're guilty, we've made a type 1 error, which is we convicted an innocent person. If we now have HA is true, they're actually guilty, and we did not reject H0, in other words, we said they might be innocent, well, that's an error. We're going to call that type 2 error. If they are guilty and we did accept HA, that means we correctly said they were guilty. And again, we want to choose H0 and HA to minimize type 1 error when we have an innocent person that we say is guilty, or we convict an innocent person. And here are some follow-on questions, like can we reduce type 1 error in the U.S. courts? And what influence does this have on type 2 error rate? And remember, type 1 error is convicting an innocent person. And so, yeah, we can minimize type 1 error. We can make the standard so high that it's really hard to convict anyone. So we'll convict less often, only if it's super, super clear that they're guilty. That will have the benefit of actually convicting fewer innocent people. But it also will end up that we're not going to convict as many guilty people either, so we're going to let a lot of guilty people go free. You know, in the most extreme example, how do you never convict an innocent person? Well, you don't convict anyone. You let everyone just always assume everyone's innocent. Of course, you don't want to do that. That's a very extreme kind of thing to do. But you never have a type 1 error that way. Similarly, you can reduce the type 2 error rate. Remember, type 2 error is failed to convict guilty people. Well, if you're worried that you're not convicting enough guilty people, you can just make it easier to convict people. And then you'll definitely convict more of the guilty people. But the problem is you'll also convict more of the innocent people. So you could lower type 2, but you're going to increase type 1 errors. So there's this trade-off, right? You can either, when you lower one type of error, you're probably going to increase the other type of error. Okay, now that we know how to set up our null and alternative hypothesis, we're going to look at hypothesis testing using confidence intervals. In particular, we're going to take a survey. We're going to use our sample statistics, p hat, as our estimate of our population parameter p, and then create a confidence interval. And from there, we're going to evaluate how probable or how likely the null hypothesis is versus the alternative hypothesis. Our first example is we're interested in how many college-educated adults can answer the following question correctly. How many of the world's one-year-old children today have been vaccinated against some disease? And this is a multiple choice question, with A being 20%, B being 50%, and C being 80%. The correct answer, by the way, is 80%, but that's really not the point of this. It's how many people can guess this correctly. And we also want to note there's a 1 in 3 or a 33% chance if you guess randomly that you'll guess correctly. So the first thing to do is to set up our hypothesis. Our null hypothesis, that's the one that kind of says there's nothing new, nothing interesting. It's very much status quo. So what we're saying then is that the proportion is going to be 33%, or pretty close to the same thing as if they guessed randomly. We're going to put this proportion with a naught to match our H naught, because there's lots of proportions here. There's P, the real proportion in the population, there's P hat for the sample. Now we have a proportion P naught that goes with our null hypothesis. Our alternative hypothesis then is that P naught is not equal to 33% or 0.333. So again, H naught says that college-educated adults really don't know how many of the world's one-year-old children have been vaccinated against some disease. So the proportion of college-educated adults who can answer this question correctly, well, they answered it correctly because they were just guessing randomly. The alternative hypothesis says the proportion of college-educated adults is either higher than the proportion you'd get if they guessed randomly, which suggests college-educated adults are informed about vaccination rates, or maybe the proportion is lower than the proportion you'd get if they just guessed randomly, which suggests maybe they are misinformed. Now that we have our two hypotheses set up, we can take a sample to test. So we take a sample of college-educated adults and find that 24% answer the question correctly. So I'm just going to circle that for now. Does the sample then support rejecting the null hypothesis and supporting the alternative hypothesis? Or does it fail to reject the null hypothesis? And we're going to answer this using a 95% confidence interval. So the idea is, one, our proportion is probably not going to be exactly 33% or 33.3%. And also, even if it were exact, a sample doesn't always hit that proportion correctly. The sample is also going to be off a little bit because of sampling error. So we want to know, is this 24% significant? Is it close enough to 33% that it actually supports it and say maybe that's just variations in the sample or sampling error? Or is 24% too far away from 33% to actually occur normally in a sample? And that's why we're going to use this 95% confidence interval. And really the first thing we do, which I did not do for this example, but I'll do for a later one, and also this is from the first section of chapter 5. We need to verify that we can use the central limit theorem, that the distribution is normal. And we do that by, one, saying that the observations are independent, and you will get that if you have a truly random sample. And two, you also show that n, the sample size, is large enough. So now that we have a sample, we're going to assume a normal distribution. We can then talk about looking at a 95% confidence interval. So I'm looking at my table here, and the z-score that I need for an area of 95%, so the 95% of the area should be shaded for this z-score. I have 94.88, which is a little bit smaller than 95, and 95.45, which is a little bit larger. So somewhere between 1.95 and 2.0 is our 95% confidence interval, and our z-score is going to be somewhere between 1.95 and 2. Your book chooses 1.96. Personally, if you were in my class, which you probably aren't because this is the internet and you're taking it from some other school, we had this 68, 95, 99.7 rule from the first section of chapter 5, which said that 95% of your data is between two standard deviations, the -2 and 2 standard deviations from the mean. So personally, I would use a z-score equal to 2, because what's the use of having a 68, 95, 99.7 rule unless you use it instead of always looking up the table. So if you've memorized this rule and your teacher lets you, good for you. You can use the 2 standard deviations or 2 standard errors for your 95%. But as I said, your book tends to use 1.96. So that's what I'm going to illustrate for you in this example, 1.96. So I'm going to write this down. We're going to assume then, we're going to take p hat and assume that p equals p hat. Okay, so we took this from our survey and it's 24% or 0.24. So how likely then is our p naught of 33%? And we said the z-score for 95% confidence interval is 1.96. To figure how many units away from the median 1.96 standard errors is, we first need to calculate the standard error. So here I have standard error is equal to the square root p times 1 minus p over n. In this case, we're going to use our p hat for our p. So we're going to have 0.24, 1 minus 0.24 over our sample of 50. So n is equal to 50 in this case, and we get one standard error is equal to 0.06. 2 standard errors would be 2 times this. So 1.96 standard errors is going to be 1.96 times our standard error. 1.96 times 0.06, it's 0.118 percentage points, or units, will be associated with our 95% confidence interval. And I'm going to draw this picture here. This is our normal curve. Our z-score is 0, right, where p is equal to 0.24. And then we're looking at minus 1.96 standard errors over to the left and 1.96 standard errors to the right. That gives us a 95% of our data. So minus 1.96 standard errors is equal to 0.118 or 11%. So that's 24% minus 11.8%. And over here, the 1.96 standard errors above the 0, that's the 0 being 24% plus 11.8%. So in other words, we're going to expect 24% or 0.24 plus or minus our 0.118. That will give us the interval from 0.24 minus 0.118 is 0.122, and 0.24 plus 0.118 is 0.385. So writing this now, our 0.24 plus or minus 0.188. So 0.24 minus 0.188 is 0.122, and 0.24 plus 0.118 is 0.385. So our confidence interval is 12.2% to 35.8%. So what we are saying is we are 95% confident, and again, the 95% comes from the fact that we use the z-score of 1.96, which gives us 95% of our area under the probability curve. So 95% confident that p, our population parameter, is between 12.2 and 35.8%, which includes then this 33% here. So it does not reject the hypothesis. It sort of supports the null hypothesis, vaguely supports the null hypothesis. So we say it does not reject the null hypothesis. And just a note, so again, the wording we say is we fail to reject the null hypothesis. We actually never fully accept the null hypothesis because we have so much kind of favoring the null hypothesis, sort of like when we favor innocence. Sometimes we may say, well, I'm not sure the person's guilty, so we're not going to convict the person, but that's not the same thing as saying I'm pretty sure the person's innocent. All it's saying is we think there's a chance they're not guilty. So in this case, we think there's reason to not reject the null hypothesis, which is slightly different than saying we think the null hypothesis is true. We'll do another example. So now we're interested in how many college-educated adults can answer the following question correctly. There are 2 billion children in the world today. How many children will there be in the year 2100, according to the United Nations? A, 4 billion, B, 3 billion, C, 2 billion. The correct answer is 2 billion. It's always C, isn't it? But again, that's not the point. The point is how many adults can answer this question. And again, there's a 1 in 3 chance that if they guess, they'll guess a correct answer. We'll set up our null hypothesis and alternative hypothesis first. So the uninteresting kind of state of normal things is, or unsurprising, is H naught is that P naught, again, P naught because now this is our guess that goes with our null hypothesis is equal to 33%. I don't know why there's this extra 3, ignore that. And then our alternative hypothesis says that P naught is not equal to 33%. Now, in this sample, we're going to take a larger sample of 228 college-educated adults. Let me just underline that. That's our N. And find that 14.9%, that's our P hat, answer the question correctly. So this is our point estimate from our sample. Does the sample support the null hypothesis, this P naught, or the alternative hypothesis? We'll answer using a 95% confidence interval. So now our question becomes, assuming our population parameter is equal to 14.9%. In other words, we're using P hat, our sample proportion, to estimate our population parameter. So let's assume our population parameter really is 14.9%. Then how likely is a P naught of 33.3%? To answer this question, we're going to assume P equals 14.9. We're going to calculate a 95% confidence interval. And the 95% confidence interval, according to our 68, 95, 99.7 rule, is associated with a z-score of 2. Your book, however, uses z equals 1.96 for the 95% confidence interval. This is sort of just a rough estimate. Your book likes to be a little more exact, so that's what we're going to do in our work. And before we go and complete this problem, I do want to review what this normal curve represents. So this is the distribution of sample proportions. So in other words, if we take 1,000 samples of these college-educated adults, each sample is going to yield a P hat. So 1,000 samples will yield 1,000 P hats. Now, if we make a histogram of those P hats, we'll see that the most common P hat is going to be the one that equals the population proportion. But of course, our samples aren't perfect. We haven't asked everyone of the college-educated adults. We've only sampled some small proportion, like 228 people. And we did that 1,000 times. But some of our samples are going to be skewed because that's just the nature of sampling. So what we expect, though, is that 68% of our 1,000 samples, so that would be 680 samples, are going to have P hats that are within 1 standard deviation of the true population parameter. We expect 95%, that's 950 samples then, 95% of 1,000. 950 samples are going to have a P hat, a proportion that is within 2 standard deviation of the true population proportion. And then finally, we expect 99.7 of those 1,000 samples, in other words, 997 samples, to have a P hat within 3 standard deviations of the true population norm. So again, this is our normal curve. And when we do hypothesis testing using confidence intervals, we're going to assume that our population parameter is equal to P hat. Now, to calculate 1.96 standard errors, first thing we need to know is what is the standard error. So I use my standard error formula, square root of P times 1 minus P over N. And again, for our P, we're going to use our population parameter P hat. So we get 0.149 times 1 minus 0.149 divided by our sample size of 280, and our standard error is 0.024, or 2.4%. So one standard error is 0.024. If we wanted 2 standard errors, we would multiply this by 2. If we wanted 3, we would multiply by 3. We want 1.96 standard errors, so we're going to multiply by 1.96. 1.96 times 0.024 0.024 is equal to 0.047, or 4.7%. And we're going to take our 14.9%, we're going to plus and minus our 4.7%. So when we subtract, we get 0.102. When we add, we get 0.196. So in other words, we have 10.2% and 19.6%. Now, because we were using a 95% confidence interval, our statement is we are 95% confident that P, I don't know why there's an if, we can get rid of it, P is between 10.2% and 19.6%. Looking at 33.3%, that's a little, it's actually way too high. So 33.3 does not really fall in this range, so we're going to reject the null hypothesis and accept H sub A, the alternative hypothesis. This just is not looking right. It's nowhere near close to our range because we're 95% confident it's no bigger than 19.6%. And at this point, I'm going to mention hypothesis testing using confidence intervals. Hypothesis testing is built around rejecting or failing to reject the null hypothesis. That is, we do not actually reject H0 unless we have strong evidence. But precisely what is strong evidence? As a general rule of thumb, for those cases where the null hypothesis is actually true, we do not want to incorrectly reject H0 more than 5% of the time. So that's what our 95% confidence interval is. This corresponds to a significance level, which we denote with alpha, of 0.05. So I just wrote this here. Our alpha, which is significance level, is equal to 0.05, corresponds to a 95% confidence interval because, as a general rule of thumb, for those cases where the null hypothesis is actually true, we're in this part of our table, the null hypothesis is true, we do not want to incorrectly reject H0, that's this here, the type 1 error, more than 5% of the time. So we want to limit our type 1 error to 5% or less. And we did say that we can decrease our type 1 error even more. We could go to a 99% confidence level. But remember, by decreasing type 1 errors, we're going to increase type 2. And vice versa. When we increase type 2, we decrease type 1. Now we're going to go into this formal testing using p-values, and we'll talk about this statement later because if I read it now, it doesn't mean a whole lot to me, so maybe it doesn't mean so much to you. But the idea is sometimes we can't use this, we cannot build our confidence interval from our sample statistics, so we use this other approach where instead of using our p-hat as our point estimate for our population parameter, we say, well, what if our hypothesis is true, and we're going to use then our p0 from our null hypothesis as kind of the center now of our normal distribution. Then we're going to say, how likely is it that we get p-hat as a statistic? So it's almost the opposite of hypothesis testing using a confidence interval, where p-hat was the center of our normal distribution. Now we're going to use p0. And in confidence interval, we said, well, if p-hat is the center, what's the probability of, how likely is our p0 from our null hypothesis? But now we're saying, no, our null hypothesis, p0 is what's true. What's the probability of p-hat? So it's a little different look on it. So our formal testing using p-values, the p-value is the probability of observing data at least as favorable to the alternative hypothesis as our current data set. And we're going to assume the null hypothesis is true. So let's do an example. So Pew Research asked a random sample of 1,000 American adults whether they supported the increased use of coal to produce energy. So we want to set up the hypothesis to evaluate whether a majority of American adults support or oppose the increased usage of coal. So the idea of the majority support of coal, well, we're just going to say majority means more than 50% of the people. And when we set up H0 and HA, so actually I should put a P0 here, H naught again represents a skeptical claim to be tested, or something that's sort of status quo or nothing new or original. So it's sort of the bland take on things. So our H naught is going to be that people are equally divided. There's no for or against, just P naught is equal to 50%. So the more interesting hypothesis, or the alternative hypothesis, is going to be that P naught is not 50%. In other words, the majority either oppose or support. The next question says, a sample shows that 37% of American adults support increased use of coal. So does 37% represent a real difference from the null hypothesis of 50%? Is it close enough to say maybe that's just kind of sampling error? Or is this a significant difference to maybe say that the null hypothesis is not correct? And what would the sampling distribution of P look like if the null hypothesis were true? So this question here, the sampling distribution, all of our hypothesis testing has been using the normal curve. So we're going to hope we can use the normal curve, but technically we really should verify that. We want to make sure we have a normal curve, and how do we do that? We verify the axioms of the central limit theorem. Remember, the central limit theorem and success failure condition, this is from our first chapter on the normal curve. When observations are independent, that's the first thing we need to verify. And 2, the sample size is sufficiently large, then the sample proportion p hat will tend to follow a normal distribution. So this is what guarantees us a normal distribution if these 2 conditions are met. So first, normally we say things are independent if we have a simple random sample. And then to figure out if the sample size is sufficiently large, we look at n times p, it needs to be greater than or equal to 10, and also n times 1 minus p also has to be greater than or equal to 10. And this is called the success failure condition. So looking at this independence, we said that the Pew Research did a random sample, so we've confirmed independence. Is it sufficiently large? Well, our sample size was 1,000 American adults, so we're going to do 1,000 times our p hat, and our p hat, or I'm sorry, our p naught, in this case, we're using p naught as our estimate of p, so we're going to plug in 0.5, and we get 500. That's also our 1,000. 1 minus p naught is 500, and in both cases, it's greater than 10. So our sample size is sufficiently large. And again, you'll notice that when we did confidence intervals, we estimated p using p hat. Now that we're doing formal testing using p-values, we're going to estimate p using p naught from our null hypothesis. And that's exactly what we did here. We used 0.5 from our null hypothesis. We did not use our p hat. We used p naught. Okay, so now we've answered this part of the question. It's kind of funny because that really was the first question to answer. And now we're going to ask, does the 37% represent a real difference from the null hypothesis of 50%? So the first thing we need to do is calculate standard error, because we're still going to use our confidence interval in the normal curve, but now instead of using p hat as our estimate for our population parameter, we're going to use p naught. So we're going to assume our null hypothesis is true. So calculating standard error now, we get the square root of 0.5 times 1 minus 0.5 over our sample size of n, 1,000, and we get 0.016. Again, here in our standard error, we use for p, we're using p naught from h naught, our null hypothesis for p. Now this is my big chance. I'm going to use the 68, 95, and 99.7 rule, which says that 99.7 of our sample distribution is going to fall between -3 and 3 standard deviations. So now 3 standard errors is 3 times the standard error, which is 0.048, which is 4.8%. So if I add and subtract 4.8% to 50%, on my lower end I get 45.2% and 54.8%. So over here I have my 3 standard deviations, actually it should probably be even more over here and more over here, I have 99.7%. Remember now, I've set everything up assuming my H naught is true. So if H naught is true for all of my samples, I expect 99.7% of my samples are going to be between 45.2 and 54.8 These are the numbers. 37% is still way lower. In fact, we should calculate the z-score of 38%. But the thing is it's extremely unlikely to get a 37% as a sample. And yet here we did. So either this sample is like really unusual or our null hypothesis is off. But again, if P is equal to 50%, then a sample yielding 37 is really unlikely. It's like less than 0.03% probable. And in fact, as I said, 37%, let's calculate what the z-score is. So 37 minus 50, it's 13 units lower than the mean. So how many standard errors is this? Well, that's 13 divided by the standard error. It's negative 8.125 standard errors from the mean. It's way out over here. Extremely unlikely. So this sample of 37%, either you've really hit every kind of unusual circumstance or our hypothesis is wrong. This sample does not support the null hypothesis. You know, I was just looking under my table for a z-score of -8. My table doesn't even go higher than 4.45 z-scores because you're already at 99.99991. So this z-score is crazy far away from what you would expect. So again, the idea is the sample of 37%, it's highly unlikely if H naught is true. So we're going to think maybe H naught is not true, and we're going to accept the alternative hypothesis. Our next example says a simple random sample of 1,028, I'm going to underline that, this is our N, U.S. adults in March 2013 showed that 56% supported nuclear arms reduction. So this is our P hat. 56%. Does this provide convincing evidence that a majority of Americans support, and let me just underline majority of Americans support arms reduction at the 5% significance level? I'll underline 5% significance level. Okay, so since we're talking about our hypothesis, our null hypothesis, when we talk about the majority of Americans, we're talking about greater than 50%. So our null hypothesis is going to be that really Americans don't care either way. That's kind of the uninteresting proposition. So our null hypothesis is P naught is equal to 50%, and our alternative hypothesis is P naught is not equal to 50%. In particular, that P naught is greater than 50%. And as I said, is 1,028. Our 5% significance level, that's alpha is equal 5%, which is achieved with a 95% confidence interval, which is achieved with a z-score of 1.96. We can calculate our standard error, and again, when we're using p-values, then our p, we're going to be using p naught. We're not going to be using p hat. That would be for regular confidence intervals. For this p-values, we're going to use p naught. So the standard error is equal to P naught, 1 minus P naught over N, our sample number, which is going to be 1.56%. So that's one standard error. And here I put our null distribution. So our null puts P naught, or 0 standard errors, at 50%. And I went ahead and calculated 3 standard deviations because that's a pretty big, that's actually a 99.7, I think, percent confidence interval. But I did just, for the sake of looking, I looked at 3 standard deviations. So that's 50 minus 3 times my 1.56 and 50 plus 3 times 1.56. And what I got was 45.22% and 54.68%. Again, I should say 3 standard deviations gives us our 99.7 area here. So that's a 99.7 confidence interval. And one thing I'm going to mention, so 3 standard deviations away, which covers 99.7, the highest number we get is 54. So this 56 is not looking good. But let's go ahead, and I'm going to get rid of this because it really is supposed to be a 95% confidence interval we're looking at. So let's consider 56%. How many standard deviations away is that from P naught? So 56 minus 50 is 6% above the mean. So we need to know how many standard errors is 6%. And 6% then divided by 1.56 gives us 6% is 3.85 standard errors above the mean. So our z-score is 3.85. I'm going to look up this z-score now on my table. 3.85, oh, it's right here. So the area under the curve represents 99.988% of our data. So this 99.98 I am going to draw. So here's our 3 standard deviation way over here at z equals 3.85. In other words, 3.85 standard errors away. We've encompassed 99.98% of all the area under this curve. That means what's left is 100 minus 99.988% is 0.012% or 0.00012 as a decimal. So this is a very small probability that we're going to get anything at 3.85 standard errors and over. And again, we should take into consideration we're talking about both sides, either higher or lower. So I'm going to write that down. That's our p-value is 0.00012. So if h naught is true, we have this then our null distribution. There's only a 0.012% chance of getting a sample with 56 as our proportion. And of course, this 0.012% is way less than 5% of the time. Remember, our 95% confidence interval or our 5% significance level says that maybe 5% of the time we'll get that. We might expect that number, but this is way less than 5%. We're talking 0.012%. It's a fraction of a percent. So we're going to reject H naught because this H naught is not supported by this 56% in our sample. And finally, we should write our conclusion, which is we believe the majority approve of nuclear arms reduction. To review what we've covered in this video, we talked about hypothesis testing for proportion. First, we introduced the null and alternative hypothesis. These are 2 competing hypotheses. Only one is true, and in fact, one of them literally says the other hypothesis is wrong. So the null hypothesis often represents the skeptical perspective, the one that's kind of safe or says there's no difference, nothing interesting happening. The alternative hypothesis says, wait, no, there's an alternative to what we generally believe or that we generally hold. And our job as data scientists is to play the role of skeptic. So before we buy into a new alternative hypothesis, we need to see some supporting evidence, strong supporting evidence. The next thing we talked about were decision errors. So often there are some errors that have worse consequences than others. And generally we choose H naught and HA to minimize what we call type 1 error. And a type 1 error is when a hypothesis is true, but we accept the alternative hypothesis instead. This is considered to be our worst consequential type of error, because remember, our alternative hypothesis is one we only want to accept when we have strong evidence. So I should maybe underline that. Alternative, we need strong supporting evidence. We kind of want to hang on to H naught. So this is the type of error we want to minimize. And the other type of error is when the alternative hypothesis is true, but we tend to sort of cling to H naught and we don't actually reject it. That's the type 2, when actually we should actually just gravitate towards HA, the alternative. We cling to H naught. And the typical example for this is the US justice system, in which case we consider it a more grave error to convict an innocent person, and we're willing to accept that sometimes there'll be guilty people who are not convicted. So the type 1 error is convicting a guilty person. The type 2 error, which we're more likely to accept, is some of our guilty people will then not be convicted. So what we did is we started with hypothesis testing using the confidence interval. So we're going to measure how likely the null hypothesis or the alternative hypothesis are given our sample. And we use our sample statistics p hat as the estimate of our population proportion p. And we also use p hat as the mean of our probability distribution. Then we use z-scores to determine the interval where we are. Often we use 95% confident that our population proportion is in the interval. And again, we base that on p hat. And then from there, we determine how likely is the null hypothesis versus the alternative hypothesis. Sometimes we can't do this hypothesis testing using confidence interval, so we use formal testing using p-values. In this case, the p-value is the probability of observing data at least as favorable to the alternative hypothesis as our current data set, if the null hypothesis were true. So in other words, we assume the null hypothesis is true. We then evaluate our p hat from our estimate and see how likely it is if the null hypothesis is true. So we assume H naught is true. We use P naught, that's from our null hypothesis, as the mean of a null hypothesis distribution. So now instead of using P hat as the center of our distribution, we're going to use P naught as the center of our distribution. Again, we're assuming H naught is true. Then, when the p-value is less than the significance level, we reject H naught, and we report a conclusion that the data provides strong evidence supporting the alternative hypothesis. And when the p-value is greater than the significance level, we do not reject H naught, and we report we do not have sufficient evidence to reject the null hypothesis. And that's it for this video. Thank you for watching.